Hello everyone, welcome to lecture 13 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on absorption and dispersion of electromagnetic waves. So here is the lecture outline. We will briefly see what Stokes parameters are. We will discuss about absorption of electromagnetic waves, dispersion relation, dispersion, different measures of dispersion, and also we will see the Kramers-Kronig relationship. So Stokes parameter, this is particularly interesting, that is named after Sir George Gabriel Stokes, who in 1852 observed that any polarization state of an electromagnetic wave can be defined by four parameters, which are also now known as Stokes parameters, given as S0, S1, S2 and S3. So what is S0? That is basically Ex0 square plus Ey0 square, that is nothing but mod Ex square plus mod Ey square. Okay. S1 will be Ex0 square minus Ey0 square, that is mod Ex square minus Ey square. S2 will be 2 Ex0 Ey0 cos phi, which is nothing but 2 real of Exey, and S3 is basically the sin phi component. So that is giving you 2 Ex0 Ey0 sin phi, that is nothing but 2 imaginary of Ex and Ey. So what are this phi? Phi is basically the difference between the two phase of Ey and Ex. So you can write it as phi y minus phi x, that is basically the phase difference between Ey and Ex. The Stokes factor can be represented in terms of unpolarized, so you write it as Sn, and polarized, that you write as Sp, parts of the light. So S will be Sn plus Sp, you can write it as this. Okay. So S0 minus square root of S1 square plus S2 square plus S3 square 0 0 0 plus, and then so this is for the unpolarized light and this is for the polarized light. So you have square root S1 square plus S2 square plus S3 square, then the other three parameters are S1, S2, S3. When you add them up, you get S0, S1, S2 and S3. It is a kind of a column vector. Okay. So these are called the Stokes parameter, the four parameters S0, S1, S2 and S3. Now what do they signify? Okay. So you can see that Stokes parameter S0 tells you about the total irradiance, that is the polarized and the unpolarized part together. S1 tells you about the intensity of horizontal or vertical linear polarization. S2 tells you about the intensity of linear polarized wave, which is basically plus 45 degree or minus 45 degree polarized with respect to x axis. Okay. And S3 tells you about the circular polarization. So let us take some example. So if you have linear polarization along x or y axis, in that case you will have S1 equals plus 1. That means the reflected wave is basically horizontally polarized, that means it is x polarized. If you have S1 equals minus 1, that tells you that it is basically y polarized, it is a vertical polarization. Now when you have linear polarization with an angle of plus minus pi by 4 or 45 degree, the parameter S2 will describe that linear polarization. So when you will have S2 equals plus 1, that means it is plus 45 degree linear polarization with respect to x axis. When you have S2 equals minus 1, it means minus 45 degree from the x axis again. Okay. Now the ellipticity, here again we are using the symbol chi, that can be used to define Stokes parameter. So chi you can define as S3 over S0. S0 is the unpolarized plus polarized light, that is the total light, right, total irradiance. So S3 by S1, if the ratio is 1, that means it is a left circularly polarized light. If it is minus 1, it is RCP, right circularly polarized light. So using this you can always find out what is the degree of polarization. That means your Stokes parameter can actually describe how much portion of the light wave is basically polarized. So that is called the degree of polarization, and it is given by I polarized over I total. So the total intensity is S0, and total polarized intensity will be square root of S1 square plus S2 square plus S3 square. So, this is like for vertical or horizontal polarization, this is for plus 45 degree or minus 45 degree polarization, this is for either LCP or RCP, right. So, all the polarized part will be here, this is the total irradiance. Okay. Now, as you can understand, the degree of polarization can be anywhere between 0 and 1. Okay. So, when it is 0 it is unpolarized, when it is 1 it means it is fully polarized light. Now, let us discuss about absorption of electromagnetic waves. So, in the previous lecture we have seen about the reflection and the transmission. Now, let us look into the absorption. So, till now we have considered the dielectric media to be fully transparent, that means they are not absorbing anything, but in reality every material will absorb in some band or the other, something like if you take glass also, which is kind of transparent for visible region of the optical spectrum, but it is basically absorbing in the UV and the infrared region. Generally, when electromagnetic wave or light propagate through a material, it will get attenuated in the direction of propagation. So, its amplitude will slowly reduce, and that because of the absorption. It means the energy is getting lost, and this loss of power, you can say, in the propagating electromagnetic wave happens because of conversion of light to other form of energy. Okay. So, sometimes they get absorbed, they transfer the energy to the phonons, that material heat up, okay, after absorption, and so on. So, one example would be the lattice vibration or heat that comes during the polarization of molecules by the medium, or during the local vibrations of impurity ions driven by optical fields. So, let us adopt a phenomenological approach to the absorption of light in linear medium. Here, let us consider a complex electric susceptibility. Okay. So, we are again using chi as susceptibility. Do not confuse between those, in the context chi is electric susceptibility, in the other context of Stokes parameter you can use that for what you have seen in the previous couple of slides, right. So, the dielectric permittivity epsilon will be epsilon naught 1 plus chi, and you have a complex relative permittivity which is epsilon r given as epsilon by epsilon naught, which is nothing but this ratio 1 plus chi. Now, this chi can have real and imaginary part. So, you can write chi equals chi prime plus j chi double prime. This is the real part of the electric susceptibility, and this is the imaginary part. Now, for monochromatic light, the Helmholtz equation for the complex amplitude u r remains valid. So, you can simply write del square u plus k square u equals 0, okay. But the wave number k itself becomes complex valued. So, this wave number will be complex valued because you can write it as k equals omega square root of epsilon mu naught. Now, you can take out this epsilon can be written as epsilon naught, epsilon and mu naught. So, epsilon naught, mu naught, and this omega can be adjusted to k naught, okay, and you will be left with only square root of epsilon r. So, this epsilon r you can write as 1 plus chi, and chi can be broken into the real and the imaginary parts. So, you can write k equals nothing but k naught is basically the vacuum wave vector or wave number times square root of 1 plus chi prime plus j chi double prime. Okay. So, this is where you can see the relationship. So, k naught equals omega by c. In some places people also use c naught. So, that you just understand that this is for wave number k naught in free space or vacuum. So, you understood the k has got a real and an imaginary component. So, you can write k as beta minus j alpha by 2, and if you allow this beta and alpha to be related to the susceptibility components chi prime and chi double prime, okay, you will see that you can write k equals beta minus j alpha by 2 equals k naught square root of 1 plus chi prime plus j chi double prime. Now, what you have to do here, you have to equate the real part with the real part and imaginary part with the imaginary part on both sides of the equations, and you can find out what each parameter stands for. So, as a result of this, the imaginary part of k, okay, because of this imaginary part, the plane wave with a complex amplitude, you can write u equals a exponential minus j k z, traveling through such a medium in the z direction will undergo a change in the magnitude, right, because there is loss. Earlier it was only oscillating, okay, and propagating. Now because of this part there will be decay in the amplitude, okay. So, there will be phase change plus there will be amplitude change as well. So, once you substitute this k with this parameter, so you just use beta minus j alpha by 2 in place of k. So, this plane wave equation now looks like a exponential minus alpha z by 2 times exponential minus j beta z. Now, when alpha is greater than 0, that means you have absorption in the medium. The envelope A of the original plane wave will get attenuated by this factor exponential minus alpha z by 2 as it propagates along z. So, what happens? The intensity, so that is the amplitude, so intensity will be proportional to u. So, intensity will actually drop by square of it. So, if you take the square, you will get exponential minus alpha z. Now, you understand why we initially started with the amplitude decaying with alpha by 2, because here you will get a simplified version exponential minus alpha z. So, this is how the amplitude decays, okay. You see the oscillatory nature and the peak amplitude decays like that, okay. This is your wavelength lambda. So, this coefficient alpha is therefore recognized as the absorption coefficient, okay, and it is also called attenuation coefficient of the medium. Now, this simple exponential decay formula for the intensity can provide rationale for writing the imaginary part of k as alpha by 2, right, because you start the amplitude as alpha by 2. So, the intensity decays as minus alpha, okay. Now, since the parameter beta is the rate at which the phase changes with z, it represents the propagation constant of the wave. So, that is from the real part, right. So, you can see the medium therefore will have an effective refractive index n that will define beta equals n k naught. So, k naught is nothing but the wave number, okay, in vacuum. N is the effective refractive index, and that gives you the parameter beta, okay. And because the effective index is n, the wave will travel with a phase velocity v p equals c naught by n. So, this also allows you to find the relationship between this refractive index n and the absorption coefficient alpha when you equate the real and the imaginary part of the susceptibility, okay. So, how you can write it? You can say that n is a complex, which is a complex quantity which has got the real part, refractive index, okay, minus j alpha by 2 k naught, okay. So, this is basically the imaginary part in the refractive index, and this is equal to square root of epsilon r. Epsilon by epsilon naught is nothing but epsilon r. Now, this is 1 plus chi, chi is complex, so you can write as chi prime plus j chi double prime, right. So, this is how the equation looks like. Now, for the case of a weakly absorbing media, you can take this as much smaller than 1. This is also much smaller than 1. So, in that case you can break it as the square root can be expanded as only within 2 terms, 1 plus half chi prime plus j chi double prime, okay. And then you equate the real and the imaginary part, you will see that your n, the refractive index, is basically 1 plus half chi prime, okay. And then this part, which is basically the attenuation coefficient based on alpha, okay, that comes out to be alpha equals minus k naught chi double prime, okay. So, if you try to find out what this looks like, this is nothing but minus alpha by 2 k naught is half chi prime. So, this is basically relating the imaginary part of the susceptibility to your absorption coefficient, right. So, now let us look into the dispersion relation. So, dispersion relation basically describes the effect of dispersion on the properties of waves in a medium. So, when I say dispersion relation is basically the omega k relationship. That means what is the relationship of wavelength or wave number of a wave to its frequency. So, normally we know that C equals f lambda, that is omega by k. Omega you can write as 2 pi f, f is nothing but 1 by time period and k is 2 pi by lambda, right. Now, in the presence of dispersion, okay, the wave velocity is no longer uniquely defined, and that gives you two important parameters called phase velocity and group velocity, right. So, what is phase velocity? That comes directly from the dispersion relation omega by k. So, Vp equals omega by k, that is also the speed, okay, and group velocity will be the slope of the dispersion curve, that is dou omega by dou k, okay. That basically tells you about, say, this is a oscillating wave, okay, and you see the frequency here as omega, okay, of the wave packet. So, you see the amplitude is varying like this. So, there are two components, you can think of omega plus delta omega and omega minus delta omega, and that gives you this pattern. So, you can find out the velocity at which this group propagates, that is dou omega by dou k. So, when an electromagnetic wave consists of multiple frequencies, and that is the case in light or radio waves, each frequency will experience a slightly different speed due to the medium's property, something like permittivity and permeability, causing it to spread out or distort, or you can say in simple terms that different frequency component of an electromagnetic wave will travel at different speed when they are passing through the medium, and that is basically the property of a dispersive medium, right. So, a dispersive medium is basically characterized by frequency dependent, or you can say wavelength dependent susceptibility, chi lambda, electric permittivity, which is epsilon lambda, refractive index n lambda, and speed, which is c by n lambda. So, dispersion plays a very critical role in many areas. In optics, you can use this dispersion to explain how prisms split white light into rainbow. In telecom, you can actually see that it affects the signal clarity and bandwidth. In metamaterial, controlling the dispersion becomes key to designing advanced devices, something like cloaks or perfect lenses. So, dispersion plays a very important role. Since the angle of reflection in Snell's law depends on refractive index, which is also refractive index is wavelength dependent. So, optical components which are fabricated from dispersive materials such as prisms and lenses, they also bend light of different wavelength by different angle, and that is why you see all these effects coming out, okay. So, this accounts for the wavelength resolving capability of the reflecting surfaces, that different wavelength has got different refractive index. So, a white light will go at the R component, red, green and blue will go at different speeds because they experience different refractive index based on their wavelength, and that will actually resolve the wavelength, separate them out, okay. So, this also explains the focusing power of the lenses and the attendant chromatic aberration in the imaging system. So, these are the optical components, as you can see, fabricated from dispersive material that could refract waves of different wavelength by different angles, okay. And this all happen in polychromatic light, that means we have multiple wavelength in the same light and they are refracted into a range of direction. Now, by virtue of this frequency dependent speed of electromagnetic waves in a dispersive media, each of these frequency components comprising a short pulse of light will experience a different time delay, and if the propagation distance between the medium is substantial, you will see a brief narrow pulse at the input will get delayed and broadened. So, you will see the width of the pulse getting much broadened because of the dispersive medium. So, typically that happens in a fiber. Okay. So, this is what happens to the red component, and this is with the blue component. So, the pulse get delayed and broadened. Okay. So, you can see that the long wavelength or the low frequency component travels faster, okay, and the high frequency component or the short wavelength, okay, will come late. Okay. So, that way it will delay and get the pulse broadened. So, how do you measure dispersion? Material dispersion can be quantified in a number of different ways. For glass optical components and broadband light that covers the visible, that is the white light, a commonly used measure is the Abbe number V. It is given as Nd minus 1 divided by Nf minus Nc. So, this Nf, Nd, Nc are basically the refractive indices of the glass at 3 standard wavelength. So, one is at blue, that is taken as 486.1 nanometer, yellow taken at 587.6 nanometer, and red taken at 656.3 nanometer, right. So, if you calculate this for flint glass, V turns out to be 38, whereas for fused silica glass the V number is 68, right. So, on the other hand, you will see if the dispersion in the vicinity of a particular wavelength lambda naught is of interest, and often used measure is the magnitude of the derivative dn by d lambda naught at that particular wavelength. So, that is how also you can measure dispersion. So, this measure is appropriate for prism, for example, in which the ray deflection angle theta d is basically a function of n. So, the angular dispersion d theta d over d lambda naught can be calculated as product of material dispersion factor, that is coming from this one dn by d lambda naught, and then you have another factor d theta d by dn that depends on the geometry of the prism and the refractive index of the material from which it is made. So, you can calculate that angular dispersion, which is d theta d by d lambda naught, right. The effect of material dispersion on the propagation of brief pulses of light is governed not only by this refractive index n, but also the first derivative dn divided by d lambda naught, okay, but sometimes also from the second derivative dn square by d lambda naught square. Okay. So, all these parameters basically they affect the light propagation. So, this is how you can calculate for the material dispersion. Dispersion again means the refractive index is dependent on the wavelength, and when your pulse is very brief, the propagation of that brief pulse of light is governed by the refractive index of n, its first derivative and also its second derivative with respect to lambda naught. Finally, we will see that how absorption and dispersion are related, and we will establish the famous Kramer's chronic relationship. So, we understood that absorption and dispersion are intimately related. Indeed, if you talk about a dispersive material, a material whose refractive index is basically wavelength dependent, that means n is a function of lambda, okay, must be absorptive and must exhibit an absorption coefficient which is also wavelength dependent, right. So, a dispersive material will also be absorptive and also it will have wavelength dependency. The relation between the absorption coefficient and the refractive index is a result of the Kramer's chronic relation, which basically relate the real and the imaginary part of the susceptibilities of the medium. Okay. So, you can see, you can write chi function of nu and chi double prime function of nu, that is frequency dependence, okay, and this is how you can write it. So that's Kramers-Kronig relationship. So this is how you can correlate the real and the imaginary part of the susceptibility of the two medium, right. So given the real and the imaginary part of imaginary component of this chi nu for all nu, so this powerful relationship basically allow you to calculate the other component. So if you know the imaginary part, you can calculate the real part and vice versa, right. And this powerful formula allow the complementary component to be determined for all nu. Okay. So Kramers-Kronig relations, which are basically connecting the imaginary part of the permeability or susceptibility like chi double prime nu and chi prime nu, can translate into relations between absorption coefficient alpha nu and refractive index n nu by virtue of this formula, that you have complex refractive index n given as small n, which is the refractive index, the real part, minus j alpha by 2 k naught, which is nothing but square root of epsilon by epsilon naught that we have seen. This is basically epsilon r, and they are related by 1 plus chi prime plus j chi double prime. So you are basically relating alpha and n to chi prime and chi double prime, and chi prime and chi double prime are interrelated via this special formula called Kramers-Kronig relationship, because if you know one, you can compute the other one for all the frequencies. So that is how absorption and dispersion, they get correlated, okay, and that is how you can understand the material property at a given wavelength, and that is very important, dispersion relation. Okay. So with that we conclude this lecture. If you have got any query for this lecture, you can drop an email to this email address mentioning the lecture title and the course number on the lecture on the subject line. Thank you.